Today we are going to try to find out the alignment. We want to compute the motion vectors. We understand that in KLT algorithm, which is used for tracking, which is known as Kennard-Lucas-Thomasy algorithm, we actually want to find out what is the alignment between the motion vectors in the consecutive frames. So if we want to do that, we need to find out a p. This p is actually the variable that tells us about the alignment or about the correlation between the motion vectors that exist in consecutive frames. So if we want to find out the p, we actually have what we have to do. We want that the difference is minimized between the warped image, which we say as I, inside this w, and the template t. Basically we want to subtract the template from the warped image, and we have to sum it up on all the pixel values, and we take the square of this difference. So this value, which we call the error, this error has to be reduced. If this error is minimized, only in this case we say that the alignment is perfect or we are getting the best alignment. So if sum of square of the difference is 0, we say that alignment of the motion vectors between the consecutive frames is best. We assume that the initial estimate of p is known. We say that this p, which is the initial estimate, that on this location the motion is happening, or this is the position where the object is existing right now, we know about the initial estimate. And what we want to find out, delta p. So we say that we know this p and we will find this delta p, and when we add both of these, then we will get the new estimate or the new location of the object. So if we replace this equation in such this above equation in such a way that with I, and which is the warped image, we add this amount of delta p, which is the addition when we are moving the object, and again we are subtracting the same template out of it, and square is a must. So on this small part of the image where we have got this delta p, we can apply the Taylor series to simplify it. Whenever we have a value and an increment in that value, we can open up this expression with the help of Taylor series. So what does Taylor series say? Taylor series say that this IWXP will come as it is, and for this delta p we will get delta I. For this I we will get a delta I, and for this delta p we will get this delta p, and for this w, which is defined actually in x and p, two variables, we will get a partial derivative. So I will not have a partial derivative, it will be simply delta I, which is in fact a partial derivative in x and y, two variables. And for this delta p, we are simply having this is the gradient, this is delta. Gradient is the combination of partial derivatives with respect to x and y, and this delta is simply the difference. And this w is written as a partial derivative of w with respect to p. So this term is opened up in this manner. This is written simply as it is, and for this I we are using a gradient, and for this delta p we are using it as it is, and for this w we are taking a partial derivative, and this template will come as it is. So I have opened up this equation in the form of this with the help of Taylor series, where the gradient of the image is actually a matrix which contains the derivative of I with respect to x variable, and the derivative of I, which is image, with respect to y variable. Now we differentiate with respect to delta p. We will differentiate this equation with respect to delta p to find out delta p and minimize the equation, and then we will equate it to 0. So if I differentiate it with respect to delta p, first of all this power of 2 will come and multiply here because we are differentiating, so the powers come and multiply. Then again we are getting this same term, that delta I and partial derivative of w with respect to delta p will come with a transpose, and the remaining term of IWXP will come as it is, and this term will also come as it is. So we are only getting a transpose out of it, and the remaining term is coming out as it is. So if I equate it to 0, basically what is my intention? I want to find out this delta p. So I'm going to equate this equation to 0 to find delta P. So this entire equation is placed equal to 0. You can see from this equation that if I multiply this transpose value with this value separately, and with this and this value separately, then there will be two equations. We can multiply this value with this. So let me show you this thing in my next writing, that I have multiplied this transpose value with that value. You see that I extracted this amount out from this equation, and I multiplied this value with this. So this is shown here. So these two are multiplied together, and for the other multiplication, which you can see here, that this is multiplied with this minus this thing is going to that hand side. So when it go towards that hand side, this minus sign will be reversed. So tx will come first and w will come later. So this is the same thing that you can see here, that tx will come first and the I value will come later. Now you know that if we multiply the transpose of gradient of I with this partial derivative of w with respect to with the partial derivative with respect to p is multiplied without its transpose, then this product is known as Hermitian matrix. You know the formula of Hermitian matrix. Hermitian matrix is always calculated by multiplying the transpose with the actual. So this will become Hermitian matrix. So if you apply it on the other hand side, if you take this Hermitian matrix to this side, it will become the Hermitian inverse, and the rest of the term, this complete term will remain as it is. This summation of gradient I with the transpose, which you remember that we multiplied on the other side as well, it will come as it is, and this subtraction term will also come as it is. So this equation overall is giving me delta P. So I was already knowing the initial estimate, and when I was able to find out delta P, I am actually able to find out that what difference is happening in my new motion vector location, and how can I align my motion vectors in my consecutive frame. If I link this explanation with the overall steps of the Lucas-Canade algorithm and the methodology of finding the alignment in Lucas-Canade, you can actually relate both these things. First of all, in the first step, we had to warp the image with the initial estimate, and you see that we actually did it. We warped this I image with W x of p, in which we say that I is now a vector which is defined in two parameters. So we did it. Then we subtract from the template. So you could see that from the warped image I subtracted the template. If you don't remember, I can show it again, that the template was actually subtracted from the image. Okay, this was what we did in the step number 2. So this is how we calculated the error. Afterwards, we needed to find out the gradient of the template, and then we had to evaluate the Jacobian matrix. So you see that in this equation, you actually, once you added this delta P, the change in the estimate, and you applied the Taylor series, then you actually needed this gradient. So this is the gradient that the KLT tracking algorithm also talks about, that you need to calculate this gradient, and you need to calculate this partial derivative. This partial derivative of the matrix is known as Jacobian, because Jacobian is a matrix which contains the partial derivatives of all the functions that are included in a vector function. So you have to calculate the gradient and you have to calculate the Jacobian. Then you multiply the Jacobian with the gradient. This is the multiplication of the gradient with the Jacobian. Then you have to compute the inverse Hessian. Of course, if you have to compute the Hessian, the inverse Hessian, then first of all you will compute the Hessian, and then from the Hessian the inverse will come out. And I told you the formula of Hessian, that how do you calculate the Hessian. Hessian is always equal to the product of the transpose of this term without the transpose of that term. So these two matrices when multiplied together give you Hessian. So this is how we are following step by step the procedure of KLT algorithm. Then in the seventh step we multiply it with the error. So this was the error equation. So the error equation is actually multiplied with this transpose term. So when you multiply this transpose term with your error, then in the end your delta p is calculated in such a way that Hessian inverse comes on this side and this transpose and then this error. So 1, 2 and 3, there are three terms. You have calculated this h dash separately, h inverse separately. You have calculated this gradient separately, this Jacobian separately. Then you multiplied these two matrices and you took a transpose of this matrix, and this is a simple difference. So when these 1, 2 and 3 terms multiply together, then you get your delta p. So on the basis of this delta p, you actually update your parameters. If I explain this same term with the help of equation, so with the help of a figure, then we actually had an image. We warped the image, which means that we converted the image into a vector file, and the vector which was defined in two variables x and p. Then we subtracted the template out of that image. So after we subtracted the template, we get an error which is equal to the image minus template. We keep this error over here and we start working from here. So for the template, we calculated the gradients. Gradients are the partial derivatives with respect to x and y. And with the help of again we also have to do one more thing, which is actually the Jacobian. We find out the Jacobian matrix for the image, for the warped image, and the image is represented by this vector w. So the partial derivative of the functions inside w with respect to x and with respect to y, or with respect to p, whatever the parameters that are defining that image, you have to find the partial derivatives of those functions. The first line represents the first subfunction, the second line represents the second subfunction. Then we multiply the gradient of the template with the Jacobian matrix of the image. In the sixth step, we find out the Hessian. For Hessian, you know that we will take a transpose of this term, and the transpose is multiplied with this, and you get Hessian. Then you invert that Hessian. Inversion, you know how to do it. You concatenate an identity matrix and you apply similar steps on the identity matrix and the real original matrix H, unless and until the H becomes identity, and the whatever result will happen on the identity matrix, that will be your inverse. So you multiply that Hessian inverse with your error, and you multiply that term with this term, the gradient and the Jacobian transpose. So you have three terms: the error, this term and Hessian inverse, and these all when multiplied together they give you your delta p, and this delta p when added into your previous p, it will update your parameters. So, and you will keep repeating these update of parameters unless and until you stop tracking. So this is how we can actually do the Lucas-Canade tracking, and this is the procedure of finding alignment in Lucas-Canade. So I hope you understand the explanation that how we find out delta p and what all steps are involved. If you have any questions, you can write them into the comments section.